could be the medical domain images that you can use, right? So, obviously in medical domain, you can have an image which is black and white. So in that case, you will have essentially a 2D image and a single channel. So you can represent that by your matrix of XY. However, on the other spectrum, you can have also medical images which are RGB images. And in that, you will have, 2D image, but the 3-channel or RGB channel. So essentially, you will need a 3D tensor to represent that image. But on top of this too, and this too is also, quite available in other domains, in, computer vision domain or, normal image processing domain. But apart from this too, you might have some specific types of representation that might be needed for you to represent medical images. For example, you might have CT volume. Okay. Now the CT volume could be essentially a 3D image with a 1 channel. So think about, it's not a pixel, it's a voxel. That's the voxel space. But you do not have color information in that. You have only whether the voxel is on or off, like a pixel. So it's essentially a 3-dimensional black and white image that you get, and that is the CT volume. So you can take a CT volume represent and you can represent that as a 3D tensor. Similarly, if you have a case where you have MRI images, right? So there you have essentially a 3D image and you also have 3 different channels, right? So you have 3-dimensional images and each channel might have red, green and blue component. So you will essentially need a 4-dimensional tensor to represent this MRI type of image. Now it doesn't matter whether you have, CT volume tensor, or if you go back to the previous representation that you have, the 2D image or the 3D tensor, on all of this input representation or on all of these different types of images, essentially you can apply the operations of convolutions, max pooling, and flattening and so on. So for all of this representation, actually the pipeline of the CNN is applicable and you should be able to apply those pipelines easily. Okay. So with that, one of the things that I want to quickly focus on is talk about a specific architecture that came out from the biomedical image processing domain, and it was published in 2017, which is called deepmedic. Okay. So deepmedic was essentially built on the architecture of CNN, but this architecture was slightly different than a classical CNN architecture that we have. And so I would want to quickly point out, and if you're interested in the application of CNN in medical domain, then you should definitely refer to this paper. This is one of the architectures which is dominant. So what they had is that essentially they had 2 different parallel CNNs which were operating on 2 different inputs. Okay, so what the input was, like you have a brain MRI. What you can do is you can take the normal resolution and you can have one parallel path which is using convolutional neural networks to process on the normal resolution. But they also felt that sometimes if you do a low resolution image and if you capture more, you will be able to capture more information that might be useful in processing the local information that is there in the images that were there. So they also created a second parallel CNN which basically took this low resolution images, right? So this was 25 times 3, so you can focus on this small region, but you can have a high, low resolution image which focuses on this, the sort of blue cube that you see in this MRI images, and then they basically use the CNN architecture which I described to you, along with the upsampling, which is another difference that we have not talked about, upsampling operation that was there, and then they connected this with a fully connected layers using convolutions with 1/3 channel. So this is not a classical type of flattening and deep neural networks. They essentially implemented using a kernel operation, so you can actually slightly change the math and you can have an operation that could be useful here, and this will allow them to do not a pixel or a voxel level segmentation, but it will be allow you to do a sub voxel or sub cube level pixel segmentation. So this was a pipeline they built, and they showed that it really performed well compared to all the other architectures that were existing for this segmentation task. So again, why I want to discuss that deepmedic is like one of the architecture which is built upon convolutional neural network, but there is a creativity here in the sense that there are 2 CNNs happening. They are agglomerating information from the 2 CNNs, and they are also doing some other tricks on top of that to create a really good semantic segmentation pipeline for biomedical pipelines that we have.